We are on to another laboratory experiment together, and in this experiment we're going to focus on something called nickel DMG. Alright, well, nickel DMG is not the most important part of this lab experiment, no way, no how. What is important though with this lab experiment is this thing called gravimetric analysis. So, what is gravimetric analysis? And I'm working in a laboratory or I'm applying for a job, and on the job application it says you need to be aware of gravimetric analysis techniques. What does that even mean? Well, gravimetric analysis basically means precipitate it and weigh it. That's it. That's all you got to do. It's just fancy terms that make us sound smart while we're working in a laboratory environment. So it literally just is taking something, making a precipitate that I'll abbreviate as PPT, and then producing something that I can then dry and I can then weigh. And I'll report the weight of it. That's all that there is to a gravimetric analysis procedure. So a little bit more detail about gravimetric analysis. Before we go further in talking about nickel DMG, what is it about gravimetric analysis that you need to know walking away from this experiment and this experience that you're getting ready to set a foot on, a journey with me, your lab partner? Okay, well, gravimetric analysis basically is a method that uses mass. Alright, so we've already talked about this, and I also just want to tie a little plug in here that basically means mass is not the same thing as weight. I just want to reconfirm this notion that mass and weight are different, but we often use these terms interchangeably. That's just the way that we do it. So mass and weight we regard as meaning the same thing, but by definition, they are not the same. Weight is really dependent upon gravity, and mass is not. Mass is how much stuff you are made up of. And no matter how much stuff you're made up of, you're made up that much stuff, and it's consistent. Weight, on the other hand, is due to gravity. So that's where the definitions are slightly different. So the reason that we use gravimetric analysis, it typically is used to measure a concentration of something or a percentage of something, and that something is what we call an analyte or an analyte. So the analyte is another fancy term that we use to describe the thing that we are looking for. That's pretty much about it. It's as simple as it gets. So we're going to have this something that we're looking for, the analyte, and we're going to be measuring the concentration or the percentage of that species that might be in a solution or a sample that's provided to me in a laboratory. So how do we do this? There are a couple of steps that are pretty common in any gravimetric analysis experiment. Number one, we're going to have to dissolve the compound. If it's given to me as a compound, and in this lab experiment it will be. So I'm going to take this compound. I don't really know the concentration of that compound or how much of that analyte is present. So I'm going to dissolve that compound up, and that will free it up in solution. So the way that I want you to think of this is kind of like salt. Salt is NaCl. Okay, that is a substance. And when I put salt into water, that salt, which is an ionic compound, will break up into the ions Na and Cl-. This is what visually makes it look like it's dissolving on us. So what happens is that the water molecule, or in other words, the solvent, will start surrounding these ions little by little, and it helps keep them away. That's really what we're doing. We're breaking up the Na plus and the Cl minus. All right, well, in this lab experiment, we're going to be doing the same thing. we're going to have a substance, and that substance is going to be a salt, but it's not sodium chloride salt. There's tons of different salts out there. We just call sodium chloride salt in layman's terms. It's kind of like a common name for it. But there's tons and tons of different salts. Well, we're going to take one of these, and we're going to put it in solution. We're going to add a solvent to it, and it's going to break it up. And it's going to break it up into the ions, the positive piece, and the negative piece. Now, keep in mind, the positive pieces are going to be called cations. Sorry, C-A-T-I-O-N. And the negative pieces are going to be called anions. Now, once they get freed up in solution, now I can take advantage of that situation. Now I can be really mean. I can be mean to that salt because what I can do now is I can precipitate what we call the target analyte out to form a solid. All right, so for instance, let's say that I wanted the sodium. I've freed it up in solution. No longer is it in a relationship with that chlorine. I mean, these things, they tried it. It didn't work out. The water came in. That's kind of like the best friends. It pulled those two species apart, and they realized that they were better off on their own than they were together. They liked hanging out with their friends, aka the water molecule, a little bit more than they liked hanging out with the other anions or cations. Well, now that they're single, now that they're alone, I think we're alone now. Do you remember that, Tiffany, from the 80s? Probably not. You're probably too young to know 80s music. Oh, that makes me sound so old. But we can take advantage of this situation. So what we can do is if I bring in some type of reagent, I'm just going to call it reagent X, like Weapon X from X-Men. I'm going to bring in this reagent, and this reagent's going to look at the target. I'm specifically picking that reagent out because I want it to react with something that I'm interested in. And what I want it to react with is maybe the sodium. I could pick something that reacts with the chloride as well. Doesn't really matter. But if I can pick something that can come in here and grab this sodium out of solution and suck it out of the solution, then this begins the gravimetric analysis. So I'm going to precipitate the target analyte out to form a solid. And the key here is no co-precipitation. That sometimes is going to be a problem for us. All right, so step one, I'm going to get a salt. Plump, there it is. Step number two, I'm going to add a solvent. And that solvent, breaks up that clump. And this goes into positive and negative pieces. It dissolves. Now step number two says I'm going to add something to this mix. Deep, there it goes. And whatever I add to the mix, I'm specifically choosing it because I want it to react with one or the other. Well, again, let's say I'm picking sodium. So this extra reagent is going to come in and it's going to start to grab that positive sodium piece. And when it does that, a precipitate clump begins to form at the bottom. Okay, well, I'm pulling that analyte out that's of my interest. And that's precipitating out onto the bottom of the flask. And now, really what I need to do is I need to get rid of the solvent and I need to filter this solution. And then the solid, I can then dry and I can weigh or get a mass of it. Well, there's a couple of things here on the list that I haven't mentioned throughout this process. Those couple of things are all math related. Yeah, there's going to be math in this one. Not much, but there's going to be a little bit of math. So number 3 says, know the formula mass of the analyte of interest. Okay, so the analyte of interest is what I'm looking for, and in this case I said sodium, didn't I? So that's like 22.99. So this will come from the periodic chart. Typically. If not, we'll have to calculate that on our own, which is no big deal. Number 4, we have to know the mass of the compound that will form. All right, so this precipitate that's here, the question is, what kind of precipitate is it going to be? We know it's going to be sodium, but what else is with sodium that made it precipitate out of the solution? Well, I'm going to have to know that. I mean, that's one of the reasons I chose to add that reagent to it. So I know what's going to form because I picked the reagent to add to that mix to get that to fall out of solution with. So we're going to have to know the entire formula weight or molecular weight of the compound. And finally, number 5 says use the percentage to calculate the mass of the analyte that is present. So for instance, I'll take the ion sodium and then I can do the formula weight of the entire thing and I multiply by 100 and that gives me a percentage. So if I precipitate out 5 grams of solid, well, only a certain percentage of that is going to be sodium. The rest of it is the other clump that made it precipitate out with, right? It's the compound. So we'll talk a little bit about the math when we get to that point, but this is where I want your mind to be at. I've got something, I'm dissolving it. I'm precipitating out that particular analyte of interest. That depends on the metal. That depends on the ion that I'm looking for, either cation or anion. I filter it, I get a mass, and I do a percent composition calculation. That's basically what happens in gravimetric analysis. All right, so just a review of solubility rules. Here we go. Here's solubility rules. So here's a table, and the table is very similar to the table that I've showed you before. And this table is broken down by the first column that we call ion, positive or negative. Most of these are going to be negatives, though, the way that the table's laid out. And then the general solubility rules. So, for instance, NO3s. If there is an NO3 involved, then all nitrates are soluble. Ding, ding, they stay in solution. It's going to be very difficult for me to precipitate out a nitrate, right? If I have something that I dissolve in a solution and that frees up NO3 and I want to use gravimetric analysis to pull out NO3, that's going to be very hard for me to do. All nitrates are soluble. So what kind of reagent can I add into that flask to precipitate out nitrate? It's very difficult. C2H3O2, those are called acetates. All acetates are soluble except for silver. So acetate is in the same kind of boat that nitrate is in. If I have an acetate and I want to know how much acetate is present, it's going to be a very difficult chore for me to go back and figure out what kind of reagent I can add into this to precipitate out the acetates. And that's because the acetates are so darn soluble. It's not going to work. Chloride, bromine, iodides, all chlorides, bromides, and iodides are soluble except for silver, lead, and mercury. Very similar to the copper qualitative lab that we did, right? We talked about pulling things out of solution. We've talked about qualitative analysis and pulling things out of solution. And this really kind of jives along with the rest of those topics. So, here's maybe my first encounter of gravimetric analysis. Let's say that I have a solution, and this solution is made up of stuff, but one of those things is silver. Silver, free, swimming around in the flask, having a grand old time all by himself. It's a bachelor kind of life. Well, I want to pull that silver out of solution. I want the silver to go. This was the very first step in the qualitative analysis scheme. Add a reagent, precipitate it out. Do you see a precipitate? If so, then this is a positive confirmation test. Well, in this case, we're taking it to the next level. Because now, based on the solubility rules, if I know that silver is present, and I want to know how much silver there is in that solution, I can play off the solubility rules. Look at this. I can add a chloride to this solution, like salt, NaCl. So I'll add chloride to this solution, and chloride's going to come in, and that silver is going to look at that chloride, and it's going to go, hubba, hubba. That's what I want to be with for the rest of my life. And silver and chloride will make a happy little marriage that we call a compound. And that compound is a insoluble solid that will float or sink in solution, depending on what you put it in. And in this case, it will sink. So the precipitate falls to the bottom, and that precipitate is AgCl. Okay, now here's where gravimetric analysis comes in. Qualitative analysis would stop at this point. Did you see a precipitate? Ding! Yes. I put a check mark beside of it. That means silver is present. And then we move on to the next step. But in qualitative analysis, in quantitative analysis, in gravimetric analysis, we have different versions, we have different forms, folks. And in gravimetric analysis, we want masses. So what that means is that I don't stop here. I then will take this solid, I will filter it just to get the solid only. I will then dry the silver chloride precipitate that I have there. And then I'll get a mass of that silver chloride. Now, let's say that I had 5 grams. Okay, I've got 5 grams of material. But not all of that is silver. Because look at this. This is silver and chloride together. Only some of it is silver. So we have to do a percent composition calculation. What that means is that I'll take the formula weight of silver, and I'll take the molecular weight of that silver chloride, and I divide those two numbers, and I multiply by a 100 to get a percentage. Okay, so let's say that this is 50%. It's not, but let's say that it is. We'll keep the calculation simple. That means that 50% of the mass is silver. Again, that's a phony number. So that means half of this weight will actually be contributed by silver. So what's half of 5? It's 2.5. So 2.5 grams would be for silver, and 2.5 grams would be for chloride. But, yet again, it's not really 50%. That was just a made-up number to give you an example to go by. I want it easy. I want the math easy in the beginning. And this is how we do it. We make up our stuff. All right. If we keep reading the solubility rules, I see some sulfates that are listed. All sulfates are soluble, except those of barium and lead and calcium and strontium. And then carbonate and phosphate are listed. Hydroxides are listed. Sulfides are listed. And finally, the sodium and potassium and ammoniums are down here at the very bottom. All right, so to give you a visual of another gravimetric analysis procedure, here is one on the screen for you. So over to the left in this picture, what you're seeing is a solution of sodium sulfate. And to the beaker on the right-hand side, this is a solution of barium chloride. So barium chloride is soluble. It breaks up just like salt does, NaCl. I know that it's soluble because, look, there's an AQ that's listed right here. That means aqueous. That means it dissolves in water. All right, so I've got this barium chloride in that beaker, and I'm really interested in this barium. I want to know how much barium's actually there. Okay, well, how would I do this using gravimetric analysis? Well, I'll go back to the solubility rules and look. I can look at sulfate right here, and it says all sulfates are soluble. They all will stay in solution, except barium and lead and calcium and strontium. Only 4. Only 4 off of that periodic chart? I think that's a pretty good reagent to choose if I'm interested in this barium. So that's why we have sodium sulfate as the reagent that we're going to be adding in. So the sulfate in this beaker is going to be reacting with the barium in that beaker, and that barium and the sulfate come together to make a happy little marriage, and that will precipitate, because the solubility rules tell me that will precipitate barium from the solution. And that's what you're seeing in the beaker. That big white cloudy stuff that's forming in that beaker, this is barium sulfate right there. So it's pulling all the barium out. And it will settle to the bottom if I give it a chance. And then in the next step, I'm going to have to filter that solution through, get rid of the solvent. I do not want the solvent here, because the precipitate is really where my barium is going to be, and that's the analyte. That's the ion of interest. And then finally over here in D, once this stuff dries, we're going to have to get a mass, and we'll record that mass value down. And then we'll do some calculations. Folks, this is all that gravimetric analysis is supposed to be. This is it. No more than that. So on a job application, on a job listing, if you're reading this material and you're reading across these big words that sound fancy, and you run across gravimetric analysis, you need to feel pretty good about that technique, because it's one of the simplest techniques in a laboratory. And this could be a make it or break it opportunity, because they might ask you about gravimetric analysis in the interview process. And if you have a person like a bachelor's degree candidate with chemistry as their background, who's never really been introduced to gravimetric analysis or the words of gravimetric analysis, they're going to be like, what are you talking about? And then they're going to look at those people and they're going to say, well, yeah, you might have taken some classes, but you probably didn't learn anything. All right, so in this example, a little bit of math review. Barium sulfate, that stuff that we precipitated out, that has a formula weight of 233.43. The barium that's inside of this compound, right, that's only part of it, weighs 133.33. So what I'll do is I'll take 133.33, which represents barium, and I'll divide it by the total, 233.43, and I'll multiply by 100, because this is a percentage. And when I do that in my calculator, I'll end up getting 57.12%. All right, 57.12% is made up of barium. That means in a laboratory, that solid that I have filtered, right? This solid that I filtered and dried, that is barium sulfate. This mass that I will get from the balance represents barium sulfate. But only 57% of that mass is from barium. So, a little more follow-up on the math. Let's say that the solid, after it dries, weighed 0.6778 grams. Okay, this is the total. That's barium sulfate. That's your precipitate. Well, you know now that 0.5712% represents barium. So if you've got a fancy calculator, you'll have to divide 57.12% by 100 to get it back into a decimal. and you'll take 0.5712 and you'll multiply by 0.6778. So when you do that calculation, you should end up with 0.3871 grams of barium from the solution. Again, the 0.6 represents the total compound. The 0.38 represents the mass of just barium. And that barium is how much was in solution. Now, there's a couple of things that we have to do to ensure that it works. Number one, you have to add a lot of reagent. This makes things precipitate out. And if you don't add enough, you could still have little barium pieces that might be in there that haven't precipitated out yet, right? So we have to go the extra step and we have to swamp it with the reagent that we want to ensure that everything there is precipitating out on me. Number two, you've got to use a reagent that only precipitates out what you want. Now, with sulfate, it actually precipitates out other things, right? And we saw that on the solubility chart. The sulfate says that it precipitates out barium. That's great. Ding, ding. That's exactly what we want. But it also produces lead. We're not looking for that. Calcium. We're not looking for that. And strontium. We're not looking for that either. But if lead, calcium, or strontium was in this solution as well, then that sulfate would precipitate those at the same time that it would precipitate out barium. We call that a co-precipitation. That's what that stands for. A co-precipitate. Meaning that it's falling out as well as the thing that you're looking for. And we do not want those co-precipitations to happen. We really only want a reagent that only targets one ion or analyte of interest. And that reagent should only pull that one out and leave everything else there. Number three, you gotta be patient. Folks, you would not believe how many times I have to tell people to go back and do this lab over again because they were not patient. They wanted to rush this system through. And if you rush, your numbers are going to be horrible, horrible. I'm going to look at them and I'm going to do that skank face of like, ew. Nope, sorry, you got to go back. You've got to go and try it again and measure everything out from step number one and go through the process all over again. Don't be that person. You have to take time. You have to be slow. Slow and steady wins the gravimetric analysis race. Next, number four, the product that you get from these gravimetric analysis procedures, they have to be able to be filtered. I know that sounds kind of silly, but very often we might end up with sludgy-like material or curdy precipitates or jelly-like material. And these things are very, very complicated to send through a filter paper and to filter the proper way. So we're really looking for precipitates that are crystalline, that actually give us jagged little crystals, like jagged little peels. Alanis Morissette fans, there you go. And if so, then I can feel good about the gravimetric analysis procedure. Next, number five, another problem area that people just stop at for some reason. I don't understand why, but they never rinse their precipitates. So what this means is that you're going to have to bring in a lot of water. You do not, or a solvent, some kind of wash solvent. Typically it's water. So in this lab experiment, you are going to want to wash. You thought your speakers were messed up? You thought it was a buffering problem? No, because you need a wash. It has to be clean. You have to soak it and douse it with deionized water. And if not, all of that other crud is going to stay behind. And the whole point of this is to get a mass. And if you do not rinse your precipitate out very, very well, what you will end up with is your precipitate that you want, plus all of the other cruddy stuff that didn't get through the filter paper because you didn't wash all the way through. Get it? All right. Next, finally, the glassware that you use in this experiment, it has to be clean. It can't be cruddy. So you want to make sure that you pick clean glassware, clean lab tools, because any of that stuff can trash behind the precipitate and you'll get extra weights because of that. And that is something that you do not want to do. In the precipitation, folks, there's a couple of things that you need to keep in mind with any type of crystal, especially if you've watched Breaking Bad. You know that it's all about the crystal shape. So in this experiment, it's all about the crystal shape. The reason we tell you to go patient is because big crystals are preferred. Big crystals are going to be a preferred type of crystal in any precipitation reaction, really. And if you end up with small little grains of sand, that typically means that you rushed a process through. That typically means that the crystals are slightly impure. They're not going to give you very good results. They might get you close where we can put good job, but try again type of thing on you. But large, big, needle-like crystals are going to be the way to go here. So big, large chunks are going to be better than super tiny little small grains of sand. And one of the reasons that this happens is that, number one, you rush it. You don't give it time to precipitate out. And number two, you have to let it come to room temperature. If you don't let it come to room temp before you sock an ice bath to it, then you typically are going to end up with smaller grains of crystals than before. So patience is a virtue yet again. All right, so an overview of the gravimetric analysis procedure. One, we're going to prep a solution. That's what we have right here. After we prep that solution and dissolve everything, we're then going to target our analyte, and we're going to precipitate that analyte out. Next, we're going to digest, which means to heat it up a little bit. Just make sure everything is fully dissolved and coming in contact the way it needs to. After we let those crystals slowly precipitate out, we're then going to filter that. We're then going to wash. Then we're going to place it in an oven or maybe in your lab desk until it dries. So this might be one of those where you pick up from here after you come back to lab for the second time. Then we're going to take a mass of that precipitate, and then we'll end up doing a few calculations in the very end for this procedure. Now, let's talk about the lab that you'll be doing. It's not going to involve barium sulfate. All right, so if you pull up the lab directions, this is what you're going to see. So let me shrink it in size so that way you'll see a better view. And it looks like it's just one page, right? I mean, there's the lab directions, pretty simple. Step 1, and it goes all the way to step 12. And then there's some questions on the back end. All right, so step number 1. Weigh 20 to 50 milligram, not gram. Please, goodness gracious, do not weigh out 50 grams of material. I say that because it's probably happened in the past. So 20 to 50 milligrams, super tiny, folks, right? I mean, 100 milligrams is 0.1, so 50 milligrams is 0.05. So this is what you want to see on the scale, 0.05 gram or lower of a selected or assigned nickel compound. So it looks like this is going to be the analyte of interest. It's my nickel. Into 4 separate beakers. 150 to 250 ml beaker. It doesn't really matter. Just get some beakers on the smaller side, and then that's what you're going to put this assigned nickel salt into. Then you're going to add 40 to 50 milliliters of deionized water. So swirl them and make sure that they dissolve. That's a key word, right? We've already talked about the importance of dissolving the salt in the very beginning. So right there, if your salts do not dissolve, you got a problem. Because if they can't dissolve, it doesn't free up the nickel. If it doesn't free up the nickel's not single. If the nickel is not single, then you can't go in and hubba the nickel in order for it to give a compound. That's the issue. Make sure it's fully dissolved. Okay, so these nickel compounds, what could they be? Well, we're going to probably give you an assortment of different ones. And not every one will have the same nickel compound. It can actually, here are just a few. Nickel 2-chloride hexahydrate, nickel 2-nitrate hexahydrate, nickel 2-sulfate. Just a few nickel compounds that we could throw out there at you. And again, yours might not be the same as your lab person that's sharing the station beside of you. So don't be looking at their numbers. Don't be cheating off of their data, because you could tattle on yourself when you do it. What are these hydrates? Well, hexa means 6 in a laboratory, and hydrate, if you hydrate yourself, what do? You drink water. So 6 water molecules. That means I've got nickel 2-chloride, a little grain of crystal right there, nickel 2-chloride, and then around that nickel 2-chloride, 1, 2, 3, 4, 5, 6 waters, all the way around, 6 water molecules. That's what a hydrate is. So there's some water weight that's assigned to these crystals, because water loves to hang out at the BFF's house, on the weekends especially. Okay, so 4 portions are going to be required. Why? Because each one of these are going to be done separate, and you're going to calculate an average. All right, so the next step of the experiment says we're going to add 0.1 gram of tartaric acid. Tartaric acid, what is that? Well, tartaric acid is actually Mother Nature found in grapes. It's kind of like part of the winemaking process, believe it or not. So tartaric acid is going to be added, and 6 drops of methyl red is going to be added. And the reason here is because tartaric acid is going to help with the chelation, or chelation, or chelation, depending on tomato type of thing. So this reagent that we're going to be adding in, again, it's not specific to just one nickel only. This could also start precipitating out other metals as well, and we don't want those metals to be present. We don't want them to interfere. So tartaric acid kind of distracts them a little bit. That's a chelation. What we're worried with here are things like chrome and iron. We don't think there'll be any chrome or iron in this, but there could be. And we're just going to take an extra little step, and we're going to throw some tartaric in just to make sure that nickel only is going to precipitate out of this thing. Now, what about the methyl red? Okay, so the methyl red indicator is going to be a pH indicator. The pH of this reaction is very important. The pH of this reaction really determines if nickel is going to precipitate out or not. Because what happens here is that if the pH is acidic, then this compound that we are going to be forming with nickel begins to dissolve. And I can't be on the acidic solution side. So what the lab directions are going to tell you to do, you're going to add tartaric for the chelation. You're going to add methyl red to get a color. It will probably be red or orangey red. And then you're going to add dilute 6 molarity ammonia, which is NH4OH. Again, that's the way that we get ammonia. And we're going to keep adding it until the color changes. Color changes? What does that mean? Well, we're going to be adding methyl red, and here you go. On the acidic side, we're going to get orangey and red. It's called methyl red. What color? Red for acidic. We don't want those colors. And the reason is because those acidic conditions will make my precipitate fall apart. I will not get a precipitate. So I need something on the basic side. So it's going to say add ammonia until the color changes. So what we're expecting to see here is something more on the yellow side. So I'm going to take a nickel compound, which looks like one of these. I'm going to dissolve it in solution. Beautiful green colors that will form from this thing. I'm going to add methyl red. That methyl red will probably show up orangey red, unless it mixes with that green color and gives us something different. But we're going to add ammonia until that color changes on me. Right? All right, next step. Heat all of the solutions near boiling. Don't worry if you boil it, you're just going to have to cool it down. Number 5, on the hot plate, we're then going to add 7 milliliters of a 1% dimethylglyoxime, or DMG. This is our reagent. This reagent's going to go in and grab the nickel and say, hubba hubba, make me a product. And that nickel's madly going to fall in love. And away they go to give me little product babies that we call nickel DMG. And only nickel will precipitate out, because the tartaric acid has helped me prevent some of those other metals from interfering with this relationship. We don't want any home wreckers. And that chromium and that iron are home wreckers. We keep them away. We want this thing to be happy. Then we're going to stir, and we're going to add 1 ml of a 3 molarity ammonium acetate. So it might smell a little bit vinegary to you. So NH4C2H3O2, there's ammonium acetate. And we will get a pink precipitate that will form. So here's dimethylglyoxime, or dimethylglyoxime. Tomato, tomato. This is its structure. I want you to think of this structure as a hand with fingers. And the fingers are here and here. Those little fingers reach out and they grab the nickel. And they form a compound. The issue here, though, it's not a one-to-one. We've seen this quite a bit in the laboratory. You might not have realized it, but it's been a one-to-one pretty much, except for here. It actually takes 2 of these to tango. So 2 of these are going to be required to bond to nickel and precipitate it out of solution. Nickel DMG, or sorry, just the DMG, it also has a tendency to grab on to palladium and cobalt as well. So yet again, we add in things like tartaric to prevent that from happening. Once the nickel gets freed up, because I've dissolved it in solution, I'll see that solution change. When I add the DMG, which is this compound here, this DMG begins to surround the nickel, and it cages it. Look at that. And it's the nitrogen pieces that reach out and grab that nickel to form this precipitate. So 1 DMG to the left and 1 DMG to the right. It told me that a precipitate would form. This is what you're looking for, folks. This is the nickel DMG precipitate right there. It's going to be reddish pink, maybe fuchsia. The solution above on the top will be clear. It might slightly be pink, but your precipitate will be reddish pink on you. If you see this, that means that you probably have done a very good job. Here's the same view, just in a test tube. So what you're seeing over the left is the initiation of the DMG getting added in. Over time, remember I told you patience is key. Over time, we start to see this precipitate begin to form. And then if I give it just a little bit more time, look at what happens in my test tube. Folks, it just completely fills up this test tube, which is why I cannot rush it. Very, very important. All right. Okay, so number 6, add 1 more ml of ammonium acetate just to create a buffer to make sure my pH is not going to change. And then let it coagulate and precipitate for at least 5 to 10 minutes. Patience. Then add 2 to 3 more drops of DMG to the liquid that sits up on above at the top, and see if you see any more precipitate that falls out of solution. If you do, that means there's more nickel that's still there, and you need to add more DMG in order to get that nickel out. Number 8, remove it from a hot plate. Number 9, after it cools, you're going to decant each of the samples through a Gooch Crucible with filter. A Gooch Crucible? What's a Gooch Crucible? Okay, never mind. I got you. So right here is what a Gooch Crucible looks like. It is a traditional type of crucible that we have in the lab that we used for heating things. And in the bottom, you'll see some holes. And the purpose of this is like a Buckner funnel. So we'll put our solution and our solid in here. We'll turn on a vacuum aspirator, and that will suck the solution out of the bottom, and all of my solid will stay up here on the top. Folks, it's just like a Buckner funnel, except they're little miniature tiny little things instead of the big bulky Buckners that we have in the lab. Okay, so after I do that, it's then going to say dry the crucibles and the precipitates in an oven at 100 to 110 degrees. Leave it in there for about an hour. Check it every 10 to 15 minutes. Or put it in your lab drawer and let it dry until the next lab period. The thing I have to say, though, is that when you begin to use the Gooch Crucibles, you need the mass. Don't forget that, please. You'll need the mass of the Gooch Crucible that I'm going to call the funnel, even though it's not a funnel, and the filter paper that you've used on the inside of that thing. You need to weigh those together, because at the end of this, you're going to have to reweigh it, and that's going to have precipitate in it. So you have to be able to subtract these two numbers from each other. Number 11, it says, using the weights, calculate and report the percent of nickel. And it says, here's my nickel, DMG, and here's the formula weight of that compound, or molecular weight of that compound, 288.92. So it's going to be up to you to figure out what is the formula weight of nickel. You can get that from the periodic chart. And number 12 says, determine the identity of your unknown based on the percentage of nickel. And we give you the possibilities that could be out there for that moment in time. Okay, so how do I do this? Well, the prior calculation, number 11, will tell you how much nickel was present in your solution. So, if you know how much gram-wise nickel was in solution, and then you know the mass number for the salt that you used, you will be able to backtrack and figure out which one of these nickel compounds was assigned to you based on percentage. So for instance, what percentage here is nickel, what percentage there is nickel, what percentage here is nickel. Which one does it match up with? Which one? And you'll be able to determine that because now you'll know the amount of nickel in solution based on the gravimetric analysis part. And you also know the start mass that you used in the very beginning. Okay, folks, so that's it of the lab. The next page here is just questions that you can answer on your own whenever you feel frisky with the calculator. And until then, I'll see you in the laboratory, or somebody will. And that's when we'll do the gravimetric analysis together. So once again, a fancy term, that means let's filter and let's weigh. That's all there is to it. Gravimetric analysis. Go home, tell somebody that's what you did today in the lab. See how impressed they sound by you. I'll see you then.